Wherever there's AMS, there's Python. Under the hood of the Amsterdam Modeling Suite, you will find a full scientific Python stack that you can use to create your own workflows. In this video, I want to show how to run and adjust such a workflow. The video is based on a step-by-step tutorial to which I put a link in the video description. The temperature dependence of the diffusion coefficient follows an Arrhenius behavior. So after calculating the diffusion coefficients at several different temperatures, we can extract the diffusion barrier from a simple Arrhenius plot. We begin by installing the Jupyter package via the AMS package manager. The workflow will run equally fine on the command line, but Jupyter Lab will allow us to inspect the code interactively and visualize the results. Once the installation is complete, use the command line to open a new notebook. Now you can either develop your workflow step by step following one of our tutorials or Python recipes, or you just import an existing one like I do here. For starters, we will look at a box of 15 argon atoms described by simple Lennard-Jones potential. The workflow itself is found in the lower half of the script. Here we loop through a list of temperatures. At every temperature we equilibrate a thermostat using a low frame rate in combination with the fast and more approximate Berenson thermostat. The equilibration run is followed by a production run with a high frame rate and a more exact Nosey-Hoover thermostat. Once all the trajectories have finished, we calculate the respective diffusion coefficients and run a linear fit through an Arrhenius plot. We can start the execution of the code by pressing Shift-Enter. It will run in parallel and only takes a couple of seconds to finish and display the results. Now let's see how we can tweak things in this workflow. I always start by locating the settings object and the molecule object. To change the engine, I just create and pass a different settings object. To change the molecule, I pass a different molecule object. Here the settings object is created and returned by function. So to switch the engine to, let's say, ReaxFF, I just add a new function that I call getReaxFFSettings. The minimal requirement for this to work is the name of the parameter file to be used. In this case, I will be using the force field file ch-argon-helium-neon-krypton.ff. Now I just swap the Lennard-Jones function calls to the ReaxFF function calls and start the calculation again with Shift-Enter. The diffusion barrier is the same here, but the outcome may vary slightly from run to run. So that's it for today. I hope you found this useful, and as always we're happy to answer any questions and comments below this video.